So today I will talk about learning-based image and video compression, recent works and perspective. So as I said before, this title was a little bit ambitious, and I added part 1 to limit this presentation to talk only on some the context requirements, and then I give some fundamental works on learning-based image coding only. I will give some performance comparison. And then in next seminar or presentation about video, about other use cases in part 2 of this presentation. So the context. So if you want to talk about the context, here I give 3 most important trends in video application. So the first one is the usual one. It's the increased usage in 2D video streaming. And this is thanks to new applications, streaming applications like YouTube, Twitch, and Netflix. And today we have around 82% of the global internet traffic is represented by video. And this traffic contributes to 1% of the global greenhouse gas emission. And this is very high. It's represent around the global greenhouse, the carbon emissions of a country like Spain. So the second trend is there is today more interest for no conventional media format. What I can say, what is not conventional media formats is new video formats different from 2D, which is point cloud, light field, 360-degree, or up to holographic. And this new format brings more realistic and immersive quality of experience up to 6 degrees of freedom. So with Hamlet, it enables us to visit the 3D scene, for example, and have more immersive quality of experience. So the third trend, which is also important, there is a recent study that showed that there is a significant increase in machine-to-machine communication. And this is new, and it is expected that half of global connected devices and connection will be for machine-to-machine communication by next year. And to give an example of what is machine-to-machine communication, we can talk about autonomous driving. For example, when we have a Tesla car taking with camera, and based on this camera, it will take important decision to speed up or to stop. And this is one example, for example of machine-to-machine communication, and there are many other. It is everything related to tasks performed by the machines. So now how we can solve this problem? So we need to compress this new formats to reduce the energy, to reduce the size, and to communicate efficiently between machines and take decisions. So the existing codec are conventional hybrid prediction and transform video standards, for example. They have been developed for more than 3 decades by ITUT, VICWAG, and ISO-MPEG standardization body. And each decade, they release a new standard. For example, AVC, which is the most famous standard in the community, released in 2003 and target HD video resolution. Then HEVC released in 2013, targeting 4K, and recently versatile video coding released in 2020, targeting a new application like 8K, 360-degree, and high dynamic range, for example. This is like one solution we have today in the table to compress efficiently this 2D video format. So what are now the limitations and the challenges of this conventional hybrid prediction transform codecs? Today, it's become very difficult to enhance the coding efficiency, not the coding efficiency, but the trade-off between coding efficiency and complexity. So it's very difficult to enhance the coding efficiency while keeping a low complexity of the encoder and the decoder. To give you an example, HEVC enables 50% coding gain, so bitrate rejection, and increases the encoder complexity by 2 times. And VVC bring the same gain over HEVC, but it increases the encoder by 8 times complexity, encoder complexity by 8 times. Today, if we want to develop a new standard, for example, for the next beyond VVC, we have to take this in consideration that if you want to get this 50% of bitrate rejection, there is an effort to put to don't increase the complexity that we can implement this codecs on different devices that can run in real time, and they can be also energy aware. The second limitation of this conventional codecs is they are optimized for 2D content, but they are not optimized for no conventional images. So, for example, when we code light field or point cloud, this solution are not leveraging all the redundancy that we can have in this content. So they are not efficient for this no conventional image coding. And the third limitation is they are optimized mostly for the human visual system. And when we talk about this codecs, they are optimized to get the highest quality of experience for human, but not for machine. And as I said, the machine is machine-to-machine communications become very important in the next years. So what we can say this solution, like conventional hybrid prediction transform codecs, are not suitable for the emerging requirement I just presented in the slide before. So now, how we can tackle these problems? So there are several solutions. So the first solution, of course, is using machine learning video coding. So machine learning have a lot of success in many applications, especially in computer vision and language processing, natural language processing. And they are used a lot in video coding also. And first I give how machine learning is used in conventional video coding. So video coding, as you probably know, it is composed in encoder and decoder. Encoder perform intra and inter prediction, transform to decorrelate the signal, and then in-loop filters to enhance the quality, and entropy encoding to remove this in the bit stream. And the decoder performs the inverse operation to recover a version of the input video. So how we can use machine learning? I give here 3 configuration. The first one, we can use machine learning as pre-processing and post-processing. So as pre-processing, we can use it that we call bitrate ladder, as it is proposed by Netflix. And the idea here is to predict what is the best resolution, best quantization parameters, or the best frame rate, for example, we can use for a target bitrate that enable us to have the highest quality. And here we can use machine learning to take these decisions and decrease the complexity, and we can run in real time these applications. The second usage is using super resolution and quality enhancement. So in the post-processing, we can perform some super resolution and quality enhancement, which is based on convolutional neural networks to enhance the video quality at the receiver side. And as pre-processing, we can also change the resolution and recover it with using this super resolution and quality enhancement module to have a better quality. So the second option where we can use machine learning, as you can see, the complexity of video codecs come at the encoder side. It is brought by how we perform the decision for the partitioning, for example, for the selection of the prediction mode, intra or enter, and which intra mode. And we can use machine learning to estimate this parameter and enhance this trade-off between coding efficiency and complexity. And the target here, for example, for VVC, we want to reach exactly the same performance than VVC, but with 1% of VVC complexity, especially targeting IoT application with very low computing resources and the memory and the computing memory and energy resources. So the third option when we can use machine learning is we can replace all these coding blocks, intra and inter prediction, especially only in-loop filters. We can replace them with convolutional neural networks to use convolutional neural network instead of handcrafted solution. This is used in the literature and it shows good performance improvement compared to existing tools, handcrafted, but of course it increases the complexity. So the last solution for machine learning in video coding is what we call learning-based image and video coding. And the idea here is to replace all these blocks or all this paradigm of prediction and transform with an autoencoder. And this will be my talk today, like the subject of my talk, focusing on learning-based image coding. So as you will see, I will present 4 different schemes and compare them. And these schemes have been the effort during the 5 last year to enhance the coding efficiency of this learning-based image coding and reach or even do better than existing conventional codecs. So first, so the idea here is to bring what we call nonlinear transform jointly with the quantization. And the principle is summarized here is in this figure. So X is the input image. So we'll use here what we call a nonlinear transform, which is represented by the function GA for analysis transform. And then we get latent space variable y, which is then quantized into y hat. And then we use entropy encoder to encode this latent variable. Here we get the bit stream. At the decoder side, we have entropy decoders. So as we can see, entropy encoder and entropy decoder is guided by a probability model P, which is constant here. And then we have here a synthesis module, which is in the decoder part that's enabled to map back the latent space to a version of the input image. We call here X hat. So this is the basic principle of learning-based image coding, which is composed by an autoencoder with 2 nonlinear transform, GA and GS, and quantization at the encoder, and entropy encoder guided by a probability model. It is very simple. Now, if you want to formalize this, so we have X, which is input image. First, we use this parametric analysis transform, GA, which is the encoder part of the autoencoder, to map the input image into the latent space Y. Then we use a quantization, and here a quantization enables to map this real values of the latent space into code words Q. We call here also Y hat. And here we just use a rounding quantization. So we will have then a synthesis block that's synthesized the input image from the latent space, quantized and encoded with entropy encoder. And here we call this parametric synthesis transform GS. So as you can see here, GA and GAs are 2 parametric functions which have learned parameters, which are theta and phi here. So now, how we can optimize this network? So the idea in a classical autoencoder, we optimize just the difference between the input and the output. And when it is for compression, we need this loss function that takes into account both the distortion between X and X hat, which is here the expectation with a distance here. It can be any distance, quadratic distance, for example, between X and X hat. And here we added also the expectation for the rate. And this part, it represents the rate. And the rate is computed here by the entropy, which is log 2 of the distribution of the code words Q. So how we can compute this distribution of the code words Q, which is just the area under the area under the curve of the density probability of the latent space y. So it is an integral for each quantized code words. We have just the integral between minus half and plus half of the density probability of the latent space yi. So the problem with this formulation is that this density probability is not continuous, and the derivative of this, so to optimize this loss functions with gradient descent stochastical models, we need that all these terms should be different derivative. And here, if we want to compute the derivative of this distribution, we will have a function that is zero almost everywhere. So this problem prevents us to optimize this network and this network with using stochastic gradient descent. So the idea that's come from Bali, pioneer work on this domain. So the idea here is to replace this quantization with an IDD noise, delta y, following a uniform distribution between 0 and 1. So the idea here is, instead of using this rounding at the training part, we use what we call here a continuous relaxation of the probability mass function Q. So what we do, we just compute y tilde, which is y plus delta y. And this delta y, it is a random variable following a uniform distribution. And this enables to have this continuous relaxation, and the loss function become derivatives, and we approximate like the effect of quantization we can have. So here we have the sum of two distributions. So now what is the density function of y tilde? It is actually the convolution between the distribution of y and the uniform distribution. This is very known formula. We study it in signal processing in the third year, like when we have a sum between two distributions. So the density function of this new distribution, it is the convolution between these two distributions. So this is solve this. It solved this problem. Yeah. Sorry. Yeah, to give an example about this three distribution, here we show the distribution of y, which is distribution of the latent space in blue, which is continuous, everything is okay. Then we show the distribution after the quantization of this py hat, which is just bound. For this reason, it is discrete, not continuous, and its derivative, it's zero everywhere. And with using this continuous relaxation, we can have this new distribution of p tilde, which is continuous and maps the quantization value of y. So this red area enables us to make this loss function derivative, and we can train this network end-to-end using famous stochastical gradient descent approach. So this is the differentiable loss function. So we have the expectation over x and over delta y. So here the first term is just exactly the SAT, which is computed with GA and GS. And the second term here, it's the rate term, which is log 2 of PYI. So this is an example of this network in practical implementation. We have an input image. Then we have 4 convolutional layers with a number of feature maps and a kernel of size 5 by 5. And then we have downsampling by 2. And after each convolution layer, we have a nonlinear operation. Here we choose a general distribution, GND distribution, which is like a nonlinear Gaussian, which is a Gaussian nonlinear operation. It is used a lot in image processing because it's enabled to have some normalization of the features following a Gaussian distribution. So this is the encoder with which is analysis transform with function GA. We have 4 convolutional layers, and each layer is followed by a nonlinear operation GND. Then we have quantization. The quantization, then the latent space are encoded with an autoencoder, decoded by the autoencoder. And here we have the synthesis transform, which is also the same operation than here. Instead of having downsampling, here we have upsampling, and here we have inverse EGDN operation, and that we can recover the input image. And all this is the parameters of these 2 networks are optimized in end-to-end, relying on the loss function I just presented in the previous slide. And we can notice here that the entropy encoder is guided with a probability model, which is fixed. It can be like normal distribution or Laplacian distribution. So this is the first work presented by Bale in, I think, in 2016. And this is model, we will call it in this presentation, the baseline model. And then after I will present only some enhancement relying on this model. So the first enhancement, we call it Hyperprior for more accurate probability model. So the objective is to reduce the mismatch between the latent variable probability model, P, like the model we use here, and the real distribution of the code words Q, like the real distribution of Y. So if we have a mismatch between the probability model P and the real distribution of the latent variable, we will have a rate overhead. And this rate overhead we want to reduce with having a more accurate probability model. And this rate overhead can be estimated with using callback divergence between the 2 distribution Q and P. So how we can have a more accurate density probability model? So the idea here is to encode and convert other hyperprior, which is called Z, used at the decoder to derive the vector of parameters Psi that will be conditioning of the latent variable. So it looks like complex, but I think I have a scheme here that give us a clear idea how we can do this. So here I put the red blocks, new blocks we added to represent these hyperpriors, and all black boxes, rectangles, already exist in the baseline system. So here in the left, we have the baseline system, and on the right, all the new blocks which are in red, they are the new ones that enable to better estimate the hyperpriors of this probability models that is used for the entropy encoder and decoder that encodes the latent space. So the idea here is to add another autoencoder with an encoder and a decoder, which is called HA and HS. So this new autoencoders, it maps the input, which is the latent space here from Y. It's mapped to a parameter Psi, which is used to guide the entropy model, which is used to encode the second entropy model that encodes the the latent variable. So of course, to send this Z to the decoder, we have of course to add quantization and also an entropy model. So this entropy model is guided with a density probability PZ, which is constant this time, but and the decoder transform, it's enabled to estimate this Psi parameter, which are hyperpriors of this density probability model that is used to encode the latent space Y hat. What we can notice here, these two autoencoders are different from these two autoencoders. have you noticed something different from this two and this two or not? I can tell you a very little difference. Here we have X. We want to map it to X at. So it's the input image, the decoded image, it's the same dimension. Here we have latent space Y. We want to map it to C parameters, which are two parameters, for example, which is the mean and the variance of this distribution. So we can notice that the domain of Y and the domain of C are completely different. So these two autoencoders are doing something different from this autoencoder. So here the idea is to map the latent space to predict the parameters of the distribution we need to use here to encode efficiently this latent space variable. Of course, we will add the rate. So here we have two bit stream. The first bit stream is used to encode the latent space, and the second bit stream is used to encode the hyperpriors, like which is Z. And from this Z, we will enable to recover the C parameters, which are the parameters of the second probability model used here. So all this network is chained into end-to-end, and the parameters of this two encoders and two decoders are also optimized jointly. With so to summarize here, we have analysis transform HA that's enabled to encode latent space into the hyperprior Z. We have quantization of Z into Z hat, and then we have this synthesis transform HS that's enabled to synthesize or predict the parameters of the distribution model used to encode the latent variable. And of course, these two parameter function have learning parameters, theta and phi, which are, of course, different from the one used to encode the latent space. Now, of course, if you want to optimize all this system jointly in end-to-end, we need to define a loss function, which is expressed as below. It is expectation over X for the distance. Always we have this distortion or distance between X and X hat. And here we have lambda, which is multiplied by the rate. So the rate, this times we have the rate corresponding to the latent variable. And we have here the rate that corresponds to the hyperpriors that is used here as also a bit stream, which is sent to the decoder. So here I give what are these hyperpriors? In practice, these hyperpriors are a couple of parameters, like here psi. It is the mean and the standard deviation or the variance of normal distribution or Laplacian distribution. Whether we can use normal or we can use Laplacian. It depends on the implementation. And here, like Py, it will follow this normal distribution of mean mu I and sigma I. So for each variable in this latent space, we will have a couple of two parameters. So we can use this formula, or we can also use the second formula. Here we just perform some sampling of the variable with subtracting the mean, and then at the decoder side we can use a normal distribution with mean 0 and standard deviation sigma. Okay, for this scheme, so if you want to give you details of this network, so we have the first network as before with encoder and decoder that's encode latent space. And here we have a second autoencoder here in yellow and blue, which encodes, which like from this Y, it's enabled to get this Z hyperprior, and from this Z, it's enabled to synthesize the parameters that's used to guide the density model, probability density model of the entropy encoder used to encode the latent space. So as I said before, we have two bit stream. What we can notice from this architecture, we can see that these two architectures are very shallow. So we have only 4 convolutional layers, and here we have only 3 convolutional layers. And here we use as nonlinear function Leakey-Rieru function. So the system, it's still very simple, and we will see later about the performance. It's bring a significant coding efficiency enhancement. So now we go to the third model, which is more complex. This time we call it auto-regressive probability model. So here it's the same. All the blocks in the black are in the previous model, and the new blocks I added here with the auto-regressive model are the blocks which are highlighted in red. So we have only these two blocks. So what we can notice before, that's when we encode hyperpriors in this distribution, we just use the hyperpriors of the current variable yi. So with the auto-regressive probability model, the idea is to leverage, to take benefits from the previously decoded latent. For example, here, what we added the y when of previous latent variable that we enter to this auto-regressive probability model R. That's enabled to compute some features, and then it goes to a fusion block, and this F fusion block, it's makes some fusion between the parameters synthesized by HS and features from the previous latent space to have a more accurate hyperpriors that are used to guide this probability density model. It's okay. So here, what we do with auto-regressive probability model is to leverage information from the already decoded latent variable, so I minus, the previous one, through two modules. The first one is the auto-regressive module that compute significant features from the previously decoded latent space, and then a fusion module that fuse these features with the features decoded with this with this synthesis decoder to have a more accurate model. So if you want to summarize, so this auto-regressive probability model, it's added two new models, F and R. So R enables to compute features from already decoded latent variable, and F, it's enabled to fuse the features from the R and features from HS to compute a more accurate hyperprior CE. See, so in practical, what is this F and R? Are just pixel CNN-like model. They are also based on masked convolutional layer, and they are also very, very shallow. They are composed only of 3 or 4 layers. But the problem with this auto-regressive probability model, it's introduced some sequential decoding. So here, if you want to decode yi, we need to have there is a sequential loop here from I minus 1, for example, and this is very bad for parallelization computing because it's added some sequential computing. So now I will give some performance about all this model. So we have a 3 model. So the baseline model with a fixed density probability, it is represented here in green. And the second model I presented with hyperprior, it is represented in red. And this curve, it gives the performance of these models when they are trained on the Click 2020 training set. And here the performance are given when they are tested on the Click 2020 validation set. And this curve, it represents the PSNR, which gives us information about the quality versus the bitrate. So we perform the coding at different bitrates. So, and here we compare the performance of the baseline model in green with fixed density probability P, and the one that added hyperpriors in red. We compare them to JPEG, which is well known, HM, which is implementation of HEVC, and VTM, it's implementation of VVC. As we can see here, both fixed density probability and hyperprior perform better than JPEG, of course, but they are slightly lower than HM and far from VVC. But what we can see here that using hyperpriors, this second model, it enables significant gain in terms of PSNR rate distortion optimization. Here, the idea of this figure is just to show like improvements that brought by this hyperprior coding, and also in comparison with existing conventional model, which are JPEG, HEVC, and VTM in terms of PSNR. Now, if we want to go further, as I said before, we have this hyperpriors, and then we added some auto-regressive model. And here I represent the same curve, PSNR in terms of rate. Hyperpriors, they are the same in red, and I added this auto-regressive model, which is in blue. It's added some significant, some gain, but not that much. But the problem with this auto-regressive model, it's added some sequential dependency that prevents from fast parallel decoding, which is not suitable, I think, in real implementation. Now, like what I presented before, like using like hyperprior auto-regressive model are the first work on this learning-based image coding developed between 2016 and 2018. And there are a lot of papers which have been proposed up to now. And there is one new paper, this is reference 5. They try to improve like the previous model. And how they try to improve the previous model. This is common in machine learning. So they added attention blocks and also deeper convolutional neural networks. So here we have more convolutions, and we have some skip connection here. And also they added some attention map. And they use the same idea of hyperpriors that are encoded to guide these auto-encoders. And also they use this auto-regressive model also to have a better estimation of the probability density of used for the entropy encoder and entropy decoder. So all the literature try to improve this baseline model, and this one, for example, which have a very good performance, it added deeper networks, skip connections, attention blocks. And also we will see a more accurate density probability model. So if we can go have a look for this attention map, it is a classical attention map with using residual blocks, which are then multiplied with another residual blocks here to just focus on the most important information in the feature maps. And this residual block are represented here. They are composed on convolutional layers and the ReLU as a nonlinear operation. As I said, they use a more accurate density probability model. They use what we call Gaussian mixture distribution. So they showed here that when we use Laplacian or normal distribution, we don't fit all the distribution of the latent space. So they added a sum of normal distribution, which is weighted with this omega. So here, then when they want to predict this psi parameters, which is composed in the classical model with the mean and the variance, in their work, it is composed in the mean, variance, and also on the weights, omega. And they enable to have a more accurate models. So this work is just to show you how research is going in this field of learning-based image coding and how they want to improve the performance of this codec to have performance better than existing model. So what we can, to summarize, we can have deeper models with more skip connection, with attention layers also, and also more accurate density probability models. So now, if you want to summarize all this work, I took this some results from the work of Timo Ladune. So to summarize, here we compute the BD rate, PSNR, which represent like the gain in bit rates on the compared to what we call here this baseline. It's the first model end-to-end learning model as presented before without this hyperpriors. This is the baseline, and the baseline is compared with different models. And here I give the features of each model, and here I give the loss in red and the gain in green compared to this model, which is the baseline, which is the anchor. What we can see here, when we don't use non-linear operation, so only convolution, for example, only linear operation, we have a loss of 63% in average compared to the baseline, which use a non-linear operation. Now, when we added hyperpriors, we have a significant gain of 32% of bitrate reduction compared to this anchor, which doesn't consider the hyperpriors. Okay. Now, when we added this auto-regressive model here, we have a significant more gain. So it is around 4 to 5% compared to the gain of compared to the hyperprior, and it enable around 36.7 gain compared to this anchor. So the anchor without hyperpriors and without auto-regressive model. So when we added this attention map and more deeper networks, we increased the performance to 55.9% compared in terms of PD rate, in terms of PSNR compared to this anchor. So we have also a significant improvement when we have more deep networks to JPEG. So the baseline is better than JPEG, and it is HEVC is better than baseline, and VVC is also better than baseline with 56.9%. When we can see that attention, the model which is based on attention models, it is performing very close to VVC in terms of PSNR. But the advantage of this learning-based model that can be optimized with any differentiable function, loss function, and especially when they are optimized with MSSCM or more perceptual image quality metrics, they perform even better than VVC, which is optimized for mean error square, which is PSNR. So this is the end of my presentation. So to conclude, so what we can say today, that we can say that learning-based image coding can reach the coding performance of the state-of-the-art conventional video standards like VVC for image coding. They have the flexibility that can be optimized for any distortion metric. As for MSSCM, we can use it also for more perceptual quality metrics. So today we can see that they perform even better than the state-of-the-art when they are trained using MSSCM and tested on MSSCM. And they have also like the advantage that can be optimized for other auxiliary machine tasks. And this maybe will be one of the topics of my next talks with also about like temporal dimension when we want to consider video. So here I give some references I cited today, and I would like finally to thank you for your attention. And if you have any question, please feel free to ask.
Thank you very much for the talk. Do we have any question? Otherwise, I can start. I have one. What about the complexity of the models that you presented? You mentioned it at the beginning that the objective was also to have a fraction of the cost of HEVC or VVC, which are becoming quite complex. What about the complexity of the networks that you presented? Are they a lot less complex, or how does it compare?
Yeah, in terms of complexity, like we did a study, we did a complete study this year comparing this 2D conventional codec with learning-based image codecs, and we have shown that they are less complex. I will talk about this also in the next talks, and we have shown, to give you idea, that they are of course less complex than VVC, for example, which is not optimized also. And it depends also if they run on GPU or CPU, and in GPU they are less complex. And finally, they are of course more complex than JPEG, for example, but this is obvious. Yeah, in the next of my talks, I will give like results which are accurate and compared in the same condition. What just I can say, like they are less complex than VVC, for example, VTM implementation, but of course more complex than JPEG.
Okay. And out of curiosity, how much time approximately does it take to train this kind of network, assuming that you have a high-end GPU available? How much time do you need to train this kind of network?
Yeah, this is a good question. Like, it is a good remark, because these networks, their efficiency depends on the training time. For example, some networks are trained for 1 week. We can get some performance, which if we train them for 1 month, we can get a higher performance. So it's very difficult to compare these networks, because this important training time will affect the performance, and usually to get the best performance, we have to train network at least for two weeks. And there are also many other problems about generalization of these models that we can also target in other talks. But usually they are trained to get this performance on, for example, 2 weeks to 3 weeks. But we can let them more, we can have some minor gain. But if we train them only on, for example, 2 or 3 days, we will get less performance.
Thank you. And so we had another question from Xavier.
Yes, thank you. Wassim, you said that the model is less complex than VTM reference model, for example. But as you know, at least for video, for real-time encoders, we reduce the complexity by a huge factor in comparison with the reference model. In this case, will we have some possibilities to reduce the complexity, or we will be sticked to the model which is proposed?
Yeah, I think we, for the complexity, of course, we have to consider optimization on GPU to do like parallel encoding and decoding. Today, I talked about image. For image, it's as we can see, it's like they are simple networks. If you want to have higher performance, we need to get more complex networks. But for video, it's even more complex, because we have a specific network for motion composition, for example. We have specific network to doing encoding of residuals or encoding of the Angela mode. So we will have like a duplicate model. For this reason, I didn't want to present today like the video part, because it is more complex. We will introduce more modules, but at least now that we know this baselines, we can go further. But yeah, the complexity is a real problem that needs to be addressed. But maybe with this technology, we are maybe targeting something at 2030. Maybe we have like the hardware and GPU, but it is not for tomorrow or 2025.
Okay. Thanks, Wassim.
Welcome.
Do we have any other questions? No. Otherwise, thank you again, Wassim, for your very interesting presentation. And we will wait for you have teased some future presentations, so we will wait for the announcement of these future dates.
Yeah, part 2.
Thank you very much, and goodbye to everyone.
Yeah, thank you.
Thank you, Wassim.
Bye.
Bye-bye.
Bye-bye.
Bye-bye.